Okay, I just wanted to go through some example problems and the basics of Chapter 13 to help you through this quiz. And there's tons of great YouTubes out there, so I'm just going to make this really quick and let you watch some of the iLectures and other YouTubes that are out there too. What we have is, we're going to start with F equals ma again. There's a couple ways to rearrange this problem. If we look at acceleration in terms of change in velocity over change in time, rearrange this like we did before, where we take the dt over to force and then integrate both sides. What we end up with is some initial linear momentum, and then we're going to apply a force, and that force is going to act on the object through some time period dt. This is impulse, and usually the dt in these cases is short for an impulse. And that will change the velocity to some new magnitude and direction at the end. So again, we have initial velocity coming in. He gets smacked with some force, and after that force is applied, he now has a new velocity. Now these guys have a magnitude and a direction here. So depending on what direction the force comes in at, that's going to influence where that second velocity is coming out at. So the main thing to talk to yourself about here is, how is the velocity being changed? Are you speeding up? Are you slowing down? How is the direction changed? All of those changes are created from that force. And sometimes this isn't just one force acting on them. This is a whole bunch of forces. Anything that changes the velocity, you're just going to keep adding all those forces together until you find everything that has changed the velocity. Anytime you see a force in any of these equations, draw a free body diagram so you can keep track of all the forces that are happening, and that's going to tell you all of the velocity changes that are happening. For our energy balance, we're going to rearrange F equals ma a little bit differently. Acceleration dv dt, but this time we're going to get rid of our time dependency by using this little chain rule. So we multiply it by dx over dx, we substitute dx over dt for velocity and f dx, so we just pull that dx over to one side, f dx equals mv dv, integrating, we get our kinetic energy, 1/2 mv squared. And of course, when you integrate it, this is 2 minus 1, or you take the initial state over here. And so what you have is you have some initial velocity, some initial kinetic energy. And in this case, instead of a force acting over a time period, it's a force acting through some displacement, just some distance. So I could call this dx, dy, ds, whatever you want to name that displacement. And this force changes the velocity into some new velocity. So we have initial velocity v1, final velocity v2. Let's talk about squared. What does this do to it? And this is the exciting part about energy balances, is negative velocity, positive velocity. When you square it, you get rid of anything to do with vectors. So it doesn't matter what direction it's in anymore. This is a scalar quantity. So do a happy dance, because you don't have to care about directions for this thing, and that makes energy balances the simple way to solve problems. If you have a choice between kinematics and kinetics and impulse momentum versus energy balance, choose energy balance, because not having to worry about direction is wonderful. Okay, so you have some initial kinetic energy. F dx is going to either speed it up or slow it down, and then it's going to have a final kinetic energy. Now, something to say about F dx. This could be work, it could be potential energy. See this summation sign? Draw a free body diagram of it and add together every single force that's going to change that energy. So you have friction slowing it down, and gravity speeding it up, and you have a motor, or you have anything that changes the velocity, you just keep adding it together. Just like you add all the x components or all the y components, just anything on there that is changing the velocity, you keep adding all those forces together. Now, if force is mg and your displacement is h, this will turn into mgh. This will turn into potential energy. Or maybe your force is kx for a spring. This will turn into 1/2 kx squared. Again, potential energy. If force is a friction, U times the normal force, then what's this going to turn into? Work. The only difference between work and potential energy, work is not a conservative force. So work depends on the path that is taken. Potential energy is independent of the path taken, and it's a conserved quantity. So whether you call this work or potential energy, just draw a free body diagram of it, add up all the forces that are acting on your system, and think about how those forces are changing the velocity. If it speeds it up, then you have to add this quantity on there. If the velocity is slowing it down, then it's negative. That's the simplest way to figure out the sign for your work, your potential energy. Just ask yourself, is the magnitude of my velocity getting larger or smaller? And again, with that v squared, all you're worried about here is the magnitude, not the direction. That really simplifies it. They give us some pretty strange nomenclature for these things. For some reason, kinetic energy uses the symbol T. I don't know where T came from, but think of some way to remember that. Maybe T is for Tigger, you know, Tigger and Winnie the Pooh, and he's always bouncing around with lots of velocity. Okay, for work, the symbol for work is U. You can remember that as ugh, work. No one wants to do work. Okay, so U for work, ugh. And then T for kinetic energy again. And again, I don't know that. And then for potential energy, they use V. Strange thing. Don't ask me why, but that's what it is. That's going to be the hardest part of this chapter, is just getting used to what abbreviations they have decided to use. Quick review about work. Force dx, it's not just the entire chunk of the force or the tire, it's only the piece of the force that is in the same direction as the displacement. So you have to break the force up into how much is in the same direction as the displacement versus how much is not. In this case, the adjacent side, the cosine side, this is the piece of the force that's in the same direction as the displacement. If you're starting here and you're going here, so remember, it is in the same direction as the displacement for the force. Here's an example problem with kinetic energy and work. What we have, a 2,000 kilogram car. Starts from rest at point A. Starts from rest, starts with a 0 kinetic energy. On a 6% incline, coasts through a distance of 150 meters to point B. Okay, starts from rest and gravity pulls it down. It's faster to point B, just coasting. The brakes are then applied, causing the car to stop at point C. Okay, so we start from rest, and then gravity pulls us down. We go faster, and then at B, they hit the brakes and stop at C. Okay, knowing that slipping is impending during the braking period, that means we're right at the edge of where that friction coefficient can't quite handle it anymore. Neglect air resistance, that simplifies it. Neglect rolling resistance. So all that we have stopping this guy is just the friction between the tire and the road. Find the speed of the car at point B. So we're just going to speed up to B. What happens here? And then we want the coefficient of static friction between the tires and the road. Even though the car is moving here, is it really static friction? Well, unless you're skidding and leaving like tread marks on the road, it's static friction. So unless you're screeching the heart and leaving tread behind, that would be static friction, but we're right on the edge of it, impending. So we are sitting right at that friction coefficient to bring it to stop. Okay, so how would you start solving this? Break it into parts. The first piece of this, from A to B. Then when we figure that out, and the fun thing about energy balances is you can start at any spot you want to start at. You can stop at any point you want to stop at, and then between your starting and stopping point, you just have to keep track of all the forces that are happening and what distances those forces are happening at. So you can jump into this system at any point, and you can leave this system at any point that is convenient for you. Let's go ahead and look at from 1 to 2. So this is part A. We're just worried about finding how fast the car is going at B. Now there's a lot of different ways that we could do this, right? This is a constant acceleration problem, so we could apply our constant acceleration equations, or we can add our forces together and look for energy balance is another way to solve the same exact problem. Energy balance is probably going to be the easiest way to solve this kind of problem. Okay, so we have starting energy. It says we start from rest, so our starting kinetic energy is 0. Force dx. So what is happening through this process? It's speeding up, right? Gravity is pulling it down, and what force is giving it this new velocity, this new energy? Well, anytime you see a force, draw a free body diagram. So what are the forces acting on this car? They said no rolling resistance, no wind drag, nothing complicated. All we have is mg acting straight down, the normal force of the road acting straight up. So go ahead and split your force into normal and tangential components. This angle is the same angle as this little 6 degrees over here. I exaggerated it so we could see it a little bit better. Okay, so mg sine theta. If you add up all the forces in the x and the y direction, mg sine theta, that's the chunk that is not balanced. The cosine piece, it's not moving it, right? The velocity is not happening in the normal direction. These forces are balanced in the normal direction. The forces are not balanced in the tangential direction, and this unbalanced force is what creates the velocity. So this time we're going to take that unbalanced force and the distance it acts over. So remember, work, it's the chunk of the force that is in the same direction as the displacement. So mg sine theta, that is the piece of it that is in the same direction as this 150 meters. So that's all we have to do. M, 2,000 pounds, G, 9.81. Okay, so there's our weight. And this is happening over 150 meters, and we have to multiply it by sine of 6 degrees. So this is the work that's happening here, and this work is responsible for the energy change. Initial kinetic energy is 0, and this will give us our final kinetic energy. Now we're dealing with mg over here. Kinetic energy, this is not weight, it's mass. So be careful for your units here. Make sure you're using masses where you need masses and weights where you need weights. But it wasn't too hard to solve for that velocity, right? So we have 0 plus mg sine theta times 150 meters equals 1/2 times 2,000 kilograms v2 squared, and you can get v2. So pretty straightforward, didn't have to worry about directions. Is that easier than using constant acceleration equations? I don't know. This is one thing you'll see in this book. It's the same problem over and over and over again with 10 different ways to solve it. And why do we have to know 10 different ways to solve it? Well, sometimes one way is easier than another way. And if you can see the simple cases, then eventually we'll get to some spots where we have 10 unknowns. Well, that means we need 10 different ways to solve it because that'll give us 10 equations for those 10 unknowns. So, but all of these methods get you to the same result at the very end, and you can apply all the methods to all the different scenarios. Okay, so there's a simple example for work. That was part A. How would we figure out the coefficient of static friction? Let's move on to part B. Here's part B. Now there's a couple different ways you could split this up. You can just look at B to C. You can look at A all the way to C. And for us, let's go ahead and jump all the way from A to C. So we're going to start with a 0 velocity again, start from rest. But now we're going to have to be a little bit careful about how we add these forces together. So what forces are happening between A and C? Well, we have gravity, and gravity is acting along the entire distance. So now that's going to be 150 plus 20, 170 meters. So we have gravity that's acting over a longer distance, and gravity is speeding it up. So for our work, we're going to have a positive sign on the gravity because it's increasing the velocity. Then we have the braking force. Now the braking force doesn't act along the entire distance. It only acts along this last little chunk. So when we add the braking force up, instead of being 170 meters, it's only acting through this last little chunk. So here we have the force from the weight, and then subtracting the brakes, it's negative because it's slowing it down. And you can add those two pieces together, and what is our final velocity? Our final velocity is 0 again. It comes to rest. So 0 plus a bunch of forces goes to 0. It's kind of strange to go from 0 to 0, but that's the starting and stopping point we had. So it ends up being just a force balance. This little braking force stops that huge gravity force, and you can solve for your static friction coefficient. Okay, so what I have is the PhET simulation going on here. There's a couple different tabs. I'm going to come over to the tab that has the force graphs, and we've got acceleration, velocity, all kinds of information we can put on here. There's also a bunch of different objects we can use. I'm going to come over here and choose the textbook. We'll push our textbook around, and next to the object it has the mass. So this guy is 10 kilograms. It has a kinetic friction coefficient of 0.2 and a static coefficient of 0.4. And the game we're going to play here is a kinetic energy and work balance game. We're going to start our object over here at -9 meters, and we're going to apply a force. And the game is we're going to push it across the floor until it reaches -2. And when it gets to -2, we're going to let go of it and let it slide to a rest. And we want to balance our force just right so that it will slide and barely not smack into this wall. Okay, so I'm going to start out just guessing, let's see, 10 kilograms. I don't know, let's put 100 newtons on there. Okay, so I'm going to push it with a force of 100 newtons, let go at 2 meters, and then watch it slide and see if it slides to a rest. And then we'll go ahead and calculate what force it would need to be, but just so you get the idea. Okay, so I'm pushing it, pushing it, pushing it, and that's not quite at -2. It's like one of those arcade games where you have to stop the thing when the light comes around to you or something. So you're going to try and stop it as close to -2 as you can, and then when you get over there, you're going to reset the force over here to 0. So that's letting go of it, and it's going to, it hit the wall that time, so we didn't get the force correct. Okay, but that's the point. You're going to push it across the floor, let go, and then it's going to slide to a rest. I'm going to go ahead and do my calculations. You don't have to use Mathematica. I'm just showing you this is my calculator. Okay, so what do we have? We have initial kinetic energy is 0. Final kinetic energy is 0. For our book, the mass is 10. Gravity is 9.81. Let's see, our friction coefficient, it is sliding around. So we're going to use the kinetic friction coefficient, which is 0.2. And what we want to solve for, here's our energy balance. So we have the starting kinetic energy, and we're going to push it with some kind of a force. I'm going to go ahead and clear that variable out to make sure that it is free and clear. And that initial force that we're speeding it up, we're going to push on it. Remember, work is force through a distance. So the distance we're going here is -9 to -2. So we have 9 minus 2, that's the distance that we're pushing it over. And we also have friction. So what's friction? U times the normal force. Normal force in this case is m times g. And the distance friction acts over, so it's not just slowing it down from 2 to the end, it's actually slowing it down the entire way. So we're going to go 9 plus, let's try and stop it at 9 meters. And this is going to equal our final kinetic energy. Okay, so this is our energy balance equation. We have our starting kinetic energy. We're starting from rest. This is our 1/2 mv squared. And then we have all of the FDXs. This is all of the work. Part of that work is speeding it up. That's pushing it. Part of that work is slowing it down. That's the friction force slowing it down. And it's going to slow it down to a final kinetic energy of 0. And we want to solve for what force we need to push it at. Okay, so just a little bit of algebra. Okay, this force should be around 50. So putting in 100, that's why it slammed into the wall. So if I try this again and I enter a force of 50.45, we'll see if it stops just before it hits the wall. That's the goal here. Okay, so I'm going to go ahead and start it at -9 meters again. And this time I'm going to apply only a force of 50.45, so a little bit smaller than I did last time. And we'll see how close to -2 I can get it to stop here. Okay, so here we go. And, well, a little short, but close enough. Okay, so I'm going to set this back to 0, and it should come to rest right before that wall. Oh! Yay, it stopped. Okay, and if I had really gone to that -2, it would have gotten even closer to that wall. So you get the point. It's friction, and there's another simulation that you actually put it on a hill, and so then you're adding in that MGH piece of it too. So play around with it, and hopefully it'll help you think through that energy balance equation a little bit better.